lead to any formal proceedings. So let me acknowledge and pay respect to the traditional owner of this country, where the city is built, which is the guiding people of the Yuran nation. So it has been and will be always there. Today, so we will have a joint distinct lecture between Sinano and Net Zero Initiative. So later I will just invite Professor Diana Diaz-Anelo, who is a professor in chemistry, very active member in Sinano, and now recently appointed as the director of the Net Zero Initiative, to introduce our speaker. Yeah. Thank you.
Look, it's an absolute pleasure to partner with Sydney Nano in this initiative, and we're absolutely delighted that we have two incredible colleagues here to meet and get to know today. So, Jan, absolute pleasure to have you here and your family. It's our delight. Jan has a very long and distinguished career at KU Leuven, from which he graduated and has been a professor since 1998, as well as being part-time at TU Eindhoven. Professor Carmeliet has over 330 papers, but I think what's really telling about the impact and influence of his work is that he's sat on a number of very influential research councils in Switzerland and around the globe, including the Research Council of the National Science Foundation of Switzerland, as well as being really the creator of many programs, including the Future Energy Efficient Buildings and District program, which I hope we can hear a little bit more about in the conversation today. Today, we're going to hear about a topic that I think we would all agree is first and foremost on the top of our minds as we head into an Australian summer and the prediction of yet a hotter summer than ever, with more and more global extremes impacting us first and foremost in our communities. And today, we're very pleased to hear your work on the impact of climate change and urban heat islands. We welcome you to the talk.
Thank you very much, and also for being here. It's my pleasure to present part of my work on urban climate and the possible mitigation. This is a collaboration, as you see, also with the University of Sydney. I will present some work of a PhD student here from Hong, and also I acknowledge Zhongling Zhao, who was a PhD student of this university, is now working at Zurich. And I also want to acknowledge Arkens Kubilai, Dominic Streli, Andreas Rubin, and Dominic. My talk will be not at a nanoscale, it will be at a very large scale, but I hope to make at least one link to the lower scales. So let me start with just taking some publicity of Switzerland, Zurich, and it says that Zurich has a climate with no excessive heat, cold, nor humidity. So it's the perfect place to live. But as you see here in a simulation of a heat wave in June, you clearly see the city center, you see the lake, you see the surrounding mountains. We are now going through the day. And this is the first day of a heat wave, and you see temperatures going up to 33, 34. It's the third day, which is the hottest day. So this is the second day. You see it cooling down to 18 degrees, so this is quite okay. So during the night, it's still possible to ventilate your buildings and have a quite good climate. But as you see with time, even during the night, the temperatures remain quite high. So we are going to the next day. You see quite high spots with high temperatures. Just this gives an image of on which resolution we are now simulating. This is 250 by 250 meters. So we don't have details of buildings included in the simulation. Later on, I will show how we do that. And you clearly see hot spots. The hot spot here is the railway station, because there are no trees, there's no shadowing, there's a lot of absorption of heat. The cooler places are around the lake, and of course these are also the most costly places to live. This is a measured signal of in the city in red of the air temperature at 2 meters, and in the rural area in blue. And you see the difference. This difference we call the urban heat island intensity. The difference between the two temperatures, which you see goes between 0 to 7 degrees. This is one of the concerns, is to keep this difference between rural area and city as low as possible. And I can already say an important observation. Somewhere the potential in mitigating the urban heat island effect is only that. It's only these 5 degrees to 7 degrees. So if you would replace the city again by a rural area, that's the temperature you can get. So you cannot get temperatures lower than the ones in blue. Right? So this is something you should understand. So that's one of my questions. Should we mitigate or should we adapt? And my answer will be in between. It's very clear that we have a lot of heat waves. This is the heat waves in Zurich since 2001 to 2020. There were 30 heat waves. You also see that the heat waves are quite different. They are not always the same. So there's also some changes due to the background climates, which can be different during these heat waves. Also, what you will notice is that there's quite some difference in definitions of what is a heat wave. So this is here a paper, as you see, together with Carmeliet and Jim Kong and John Lee, on a review on how heat waves are defined. And you see there are quite some differences as well in which metric we use: maximum temperature, minimum temperature, the intensity, is it above 30 degrees, is it above 37 degrees, and also duration. In Switzerland, we say a heat wave is when we have a temperature for 3 days above 30 degrees, which is of course different for different countries. What's the origin of the heat wave? And I have to say there are different origins of heat wave, but this is a typical one. A typical one is that you need to have high temperatures, no clouds, and then there should be a cap above this high temperature zone of a high pressure system that prevents that buoyancy can happen. So the hot air goes up but is deflected down again. So you have a circulation, which we also call a heat dome. And so it's a buoyancy driven heat dome. I will also show that here in Sydney you can find these heat domes during waves. An example of a heat wave in Europe was 2003, the summer heat wave, where you had temperatures more than 10 degrees higher than normal, and you had an excess of mortality. So what you see there is the percentage excess mortality, and you see it goes up to 150% higher. Now what is important to see is that normally you would expect, after that a lot of people died, that there would be what we call a harvesting project. That means people that would have died, will have died after. Right? But you see there's no harvesting effect. So it means that this is really causing extra deaths. And people are dying much earlier than before. And if you compare this with earthquakes or other disasters, this is a very hidden, not well known source for of course, this is only during a short period. You see here 2 heat waves. You see the number of deaths per day in Switzerland, and you see you have an excess here of 50 for the 203 and 2015 heat wave. Now what is interesting to see is that this is an excess mortality of 7%. And if you look at the age groups, it's especially people that are above 80 plus, that are very susceptible, but also people between 40 to 60 years old can be very susceptible to these heat. So what we try to do is that we try to design mitigation methods using a multiscale approach, because we have to start from the mesoscale. So we do simulations at a scale of 200 kilometers or larger, where of course it is not possible to model all the buildings. So there we use an urban parametrization, But we scale down and we go to the neighborhood scale, 2 kilometer size, where we use CFD, computational fluid dynamics, where mainly at that scale we only look at wind and heat, but then we go also to micro scale, to building scale, local scale, what we call, where we also model moisture, humidity effects. Why? Because you have also trees. Trees use water, they have transpiration, they have transpirative cooling. You can have wet materials that dry and have evaporative cooling. So this is somewhere the link we do from higher scale to lower scales. I will first start talking about some observations, then I will talk about the large scale simulations, the mesoscale simulations, and then about the local climate, microclimate simulations. Some observations. I will skip between cities. I will go from Europe, but I will also come to Australia, Sydney, and show that somewhere, of course, the background climate is different, but there are a lot of similarities. I will try to indicate that. So here what you see is the monthly maximal urban heat island intensity. So per month, we calculate the difference between the air temperature in the city, in the rural area, and we take the maximum. And you see it varies between 4 to even 11 degrees. So there's quite some variety. So this is typical. Weather is stochastic. But what you see is that there's an increase over the last 30 years. There's a clear trend that this urban heat island intensity is increasing. You see the same trend if you look at the heat wave days per month. So these are when the temperature is above 30 degrees. You clearly see that there is a trend of increasing due to climate change. Mostly people look at air temperatures or surface temperatures because they are easy to measure. I will also introduce here a metric which is called cooling degree hours. So you see a signal of the air temperature, and we take somewhere a base temperature and we calculate the red zones. So these are the hours multiplied by the how much temperature is above this base temperature. So this is an indication integrated over time of how severe your climate is. And you can do this per year. So we did this here per year, and you clearly see that there's, as well in the rural area as in the urban area, an increase. In the urban area, there was over the last 30 years an increase in 95%. So that means that more or less there's a doubling in cooling energy. But it's not so much, it's around 60%. So it a little bit over predicts, but it really shows there's an increase in cooling demand in Zurich. In the rural area, it's only 65. We did this for different cities around the world. Montreal, the increase is 68%, rural increase 46%. Chicago, quite similar to Montreal. But you see that there the trend lines are a little bit the same, only shifted. We also looked at Sydney, and we see that there in the urban area there's an increase of 90%, rural area 65%. So that clearly shows that all over the world, and I agree these are quite similar cities, well, they are different but with a similar climate, you have a clear increase in the need for cooling. And that this increase is much higher in cities than in the rural area. This is connected, of course, to developments in the city, and also due to climate change. So there's a combination of the two. You also see that the population is increasing. So it's a combination of a lot of effects together that makes that this difference between rural area and city is increasing. And this is what we want to bring back, right? We want to have these lines parallel to each other. And we don't want that with time and with climate change and with the development of our cities, that this difference between rural area and city becomes larger. Again, I say The rural area is somewhere where we want to go to by mitigation. The rest of the increase is adaptation. We have to adapt. Good. I show you now another city in Switzerland, Geneva, and I want to introduce to you that in cities you can also have quite some differences. So we call that hotspots. So you can have local heat islands in a city. And we want to understand why this happens. And if we understand that, we can also propose mitigation measures to stakeholders like cities. So this is, I don't know who has been in Geneva, but it's at a lake. And you see there's quite some vegetation. There's also quite some building area and also impervious areas. Impervious areas are roads mainly. So that means no water can go through and so no water is stored. Can be also parking not sensible. We looked at from 2019 to 2022, there's a satellite growing over Geneva every week at the same time. Luckily, it is at 12 o'clock. And so we have photos of the surface temperature. And so you collect all those days which are quite hot without clouds, and you take the average. And this is the map you get. So these are measured data of surface temperature. You clearly see the hot spots, and I hope you see that if, for instance, this hot spot is really where you have a lot of buildings. This hot spot here is an airport, where you have, of course, a lot of concrete surfaces. You clearly see the rivers which are forward and the lake. Okay. I will not explain how we did this clustering approach, but we look at building morphology, we look at land use, how the land is used, how big the buildings are, what's the morphology, height, and so on. And we do a clustering approach. And we found that Geneva you can identify by 7 clusters, which go from blue to red. Red, as you see, is here, which is the hot area. Blue is the more cool area. So we go from 1 to 7, and you see if you take the average temperature per cluster, and of course some deviations, you clearly see that cluster 1 is the coolest one, cluster 7 is the hottest one. And there's a clear trend from one to the other. You can also identify those clusters, how they look like. And you see here, cluster 1 is very green area, until cluster 4, there are quite green areas with some buildings. And then you see you get large buildings, more railway tracks, more roads, and so you get here an increase of buildings and impervious area. And so we could find the most influencing factors. And the 4 most influencing factors is building density or the building's land covered area. You clearly see that we go from blue to red and it increases, the surface temperature increases. This has a lot to do with increasing heat storage. I will come back to that. You see that also the impervious surface land covered area, if this increases, you have an increase in temperature, and you see that it's typical from blue to red, from cluster 1 to 7. This has to do with the lack of evaporative cooling. If you increase the vegetation, the surface temperature decreases. This has to do with shadowing and evaporative cooling. And what is also interesting is the sky view factor. So you take buildings and you take trees and you look up at the sky and you see how much percentage you see of the sky. If it's 1, it means you completely see the sky. If you are under a tree, like the red zones here, of course you don't see the sky, it's 0. And you clearly see there's also a clear indication that how much solar radiation can come to the surface has a big influence. So this is the sky factor. By the way, it's the most important one for Geneva. Now, out of this study, which is just, it's quite simple to do once you have the software and you have the setup. So you can easily do it also for Sydney. You can get some quite interesting conclusions you can give to the stakeholders, to the cities. For instance, we see if you would change 25% from vegetation in cluster 1 to impervious surfaces, your temperature would increase to 2.5. Compare this with this 5-6 degrees of urban heat island effect. You see, we are only half of that. With in cluster 2 to 5 is cluster 3. What is interesting here is you would change vegetation to buildings and you increase the height. You would say, oh, but higher buildings have more shadowing. But there's also less wind, less cooling by wind, by ventilation. So it's always very complex. And what you see is here for Geneva, it would increase the temperature to 4 degrees. So they are now planning in the center of Geneva some high-rise buildings. So of course, when I showed this to the urban planners, they were a little bit shocked. They said, yes, we need a study, we will pay you a study to do, because it's still very difficult to convince stakeholders and cities to do a complete study if they do a project. Of course, there's some simulation time, some work to be done. It's very strange for structural engineers, they always have money, but for climate, urban climate engineers, it's always more difficult to get something. We also learned that at least 20% should be vegetation. Otherwise, we get really these hotspots. So this is the minimum you can get and that you should have. And there are some spots in Geneva that don't have 20%. So what did we learn? I think it's clear that there's a worldwide trend of hotter summers with heat waves, that climate change intensifies the urban heat island effect, so it means cities become warmer and warmer compared to the rural area. Building densification, which is one of the aims of cities still, we should be very careful about it because it leads to higher temperatures. And we clearly see that vegetation can really, can partly be a solution. But we don't understand still a lot of things. Why we have this variation inside cities, and for that we have to go to a heat balance. Now, if you want to calculate the heat balance for a city, you need some simulations. You have to do a simulation. You cannot just be based on local methods. And that's what we do here in the meteorological Monday. I will again start with the case study of Zurich, and then I will go also to Sydney. I will just show you some results for Sydney. As you know, we get every day weather predictions. So there are models that are based on a general circulation model of the complete Earth. And then this is downscaled to what we call a regional climate weather model. So our predictions are done by those models. Now, those models don't incorporate cities. So what we do is we take such a weather model and we couple it with a parameterized model. Very simply, we say there's a city, it has a different roughness, it has a different heat storage, and so on. So we change the properties of those cells that belong to the city. You can even do a further parameterization by urban canopy models. I will not go into the details. For that, we need a downscaling from these weather models, and we want to go to a city. So this is the domain, the normal domain of a weather model, where the size of the grid size can be 6 kilometers or more, and so we have to downscale. This already takes some calculation time to do that. And so we go to 250 meters. We don't go to lower than 250 meters because then we get some noise effects. So then the model is really at its limit. Okay, we do a downnesting from the global models. And so you get a simulation of that again for the city of Zurich, for a heat wave, together with the wind patterns, so you can also see what happens with the wind, how you have wind effects that also have effect on heat removal. And so that allows us then to analyze more in detail what is happening. Just to show you here the average temperature at night, at 12 p.m. And you see that during the night here in Zurich you have 22 degrees for that heat wave in 2015. We had heat waves up to 28 degrees already. And you clearly see that here you have a hotspot. So the city is clearly warmer and you have cooler mountains. This is important. We have cooler mountains that surround the city, and probably we can have a positive effect during night. Some screenshots, you see it's quite hot here, up to 40 degrees in the city. Of course, it cools down again to lower than 20, around 20 degrees, which is good. Now, the last heat waves we had in Europe, there was no, in Spain and Italy, there was no cooling down during night, and it remained at 28. That means you suffer also during night. There's no time to, if you had a hot day, you want to have a cool night to sleep. So if it's above 26.5 degrees, we say, it starts to work on the body. So that's something we try not to have. But you see that during some heat waves, you have this possible passive cooling effect is gone. Good. Oh, sorry, still lost. To show that you have also locally these heat domes, this is on the city of Zurich, and you will see that now, somewhere here, you see those heat domes, also these local heat domes appearing, but there's also some wind, so the heat dome is also moved away, and so they appear from time to time. This we can do by calculating the height of the planetary boundary layer. So we can try to understand what local is really happening and why you have during the day hotspots. One thing to say is that if you do these calculations with these mesoscale models, trying to predict the climate in a city, we get errors between 2 and 3 degrees Celsius air temperature. You could say this is quite a lot. So what we do now is in a lot of cities, you have a network of stations where the air temperature is measured, high quality, low quality, a lot, a little bit mixed. But you can use machine learning to, you see here is the root mean squared error. What we have, if we don't do some machine learning, you can reduce this error to less than 1 degree. So this is also something we do. We do predictions of a city, but then of course we correct, we calibrate the model so that it is more accurate. And you get, for instance, a map for Zurich of the cooling degree hours. So this was this integrated value of a temperature above a certain level. This temperature, you clearly see where it is hot. Also around the lake here, you have quite some villages with quite some buildings where it is more hot. You can correlate it, for instance, to soil sealing. You see a clear correlation between the two. You can also correlate it to densities, where you have buildings, you clearly see there's a correlation. So we get a lot of information now in understanding what is happening. What we do also is to look how much the city is warmer, or how much cooling degree hours higher level you have compared to the surrounding. You see here in Zurich, which is not a very hot city, that compared to the surrounding, you go up to 8%. So it's 8% higher. We did it for Paris, also 8%. Paris is a completely different city than Zurich, but you see it's quite similar in behavior. We did Chicago. It's less, it's only 40 degrees. What is interesting here, you have the city, you have quite some influence of the lake. So there's really around the lake much lower temperatures. And you also see here this hot spot here. So the city is hot, but also this region is hot. I was some time ago in Chicago. I asked people, is it there? And they say yes. There are swamps. It's hot there. It's not. You should not buy your house there. So they know it. So they know that this is a less good area. We also did some more study on Montreal. Montreal is a city surrounded by quite some rivers, and we were interested, what is now the influence of this river? And we did first a simulation of the cooling degree hours. The relative change is up to 40%. We clearly see here a higher region where you have higher temperatures. And this is the real scenario where you have a river. We did then a crazy simulation where we said, let's just fill the river with urbanization. So what happens if I would fill this city totally, this river totally with buildings, or if I would put there forest? What is the difference? Of course, these are not realistic scenarios, but it gives some insight what could be the influence. And that's, you see here again the cooling degree hours, the relative change, and you clearly see here the river, but you see clearly hotspots around in the river. If you replace it by the city, everything becomes hot, and the hotspot even becomes more hot. If you replace it by a forest, it's better than the river. So a forest is better than a river. The reason being that you have also shadowing effects. So the air going to a tree, to a forest, is cooler than what is going above. Good. I said we should study the heat balance. The heat balance is quite simple. You have radiation coming in, there's some reflection of radiation, there's long wave radiation, so you take all this radiation together, which is incoming. You remove the sensible heat. This is heat which by convection is removed from the surface and goes back in the air. And latent heat. Latent heat has to do with evaporation, or transpiration from trees, from water bodies. Okay? So to evaporate water, you need energy. So if you evaporate water, you take energy out of the surroundings so it cools down. And for instance, you see here those fluxes calculated for Zurich. During the day, you have a lot of sensible heat. So this is the heat coming from the surfaces, and that's what you feel. So if you walk around, you feel the radiation from the hot buildings and also the sensible heat, which heats heat out of the air. The latent heat flux, here you see it's cooling down during the day. During the night, there's no latent heat flux, so the trees' evaporation almost stops. So that means that vegetation really works mainly during the days, in daylight. This is then the heat storage flux during the heat wave. You see it is quite different over the city, and that explains why you have hotspots. So some locations store the heat much more than others. That's what it is. We looked at 6 positions in Zurich, and position 4, 5, and 6 up in Lakeside Park are cooler regions, while downtown, industrial, and outtown are more hot. And we look at the heat wave. This is the measured heat wave. You see that here you have quite some days with high temperatures. We looked at the incoming radiation. Everywhere is almost the same. Okay, so incoming radiation and long-wave radiation losses. To compare this, there are some small differences, but it means everywhere you get a lot of radiation coming in. The sensible heat is also a little bit the same, but the main difference is here in the latent heat. You see that the park here and the uphill here has most latent heat, so it's cooling down the most. Then followed by the lakeside and the park. And you see the city has less latent heat. That results in the heat storage, and you see that there's a ramping up for all the sites of the heat storage. That is very typical for heat waves. So there's a pre-heat wave period where you have already a lot of storage of heat. It's not yet too hot, but you have already a ramping up of this, and this creates that you have very high temperatures during the heat wave. And that's why you have this urban heat island effect, which is much larger than a rural area, because you store a lot of heat that is not lost anymore during the night. During normal time, you have almost all the heat which is stored is lost during the night. That's when you have no heat waves, the non-conditions. So we did this also, Jim and Tom did this study for Sydney. Okay, you have again this downscaling. What is, you know better than me, but what is particular in Sydney is that it's surrounded by a lot of forest and savannas. And these here are the blue mountains, which are quite high. These are the simulation results. You see the pre-heat wave. It's heating up during the pre-heat wave. You clearly see here the city. which is much warmer, with the exception of the city at the coast where you have probably the sea breeze, which is cooling down. And then post-heat wave, it's all gone, right? You don't see anymore this heat dome here. You also see the heat dome here during the heat wave, during the night. So you have temperatures of 30 degrees, which is quite high and above the comfort. We also looked at the cooling degree hours maps. You clearly see here in the city, there are some valleys which are also quite hot. During the night, you clearly also see here, sorry, this is the change in cooling degree hours, and you see that, again, it's around 70%. So comparing with the 80% that we found before, so it seems all those cities behave quite similar. We looked also at what happens at different locations in the city. So city here, Greater Paranata and Western Sydney Airport. You see that those two here are warmer in the pre-heat wave. After the heat wave, the temperature difference is small. But you see there's a big difference between the cooling degree hours here in those two positions, and the Sydney city is quite low, so it's quite cool. So you can study all these differences and you try to understand also why this happens and what are the possible mitigation measures. Again, we look at latent heat to have the heat storage. You see there's a lot of latent heat very near the forests. Okay. In the city, there is not a lot of latent heat. We looked at three areas, urban, forest, savannas, and you clearly see that in urban there's no latent heat, in the forest there's a lot in the savanna, and that explains the difference of how much heat is stored. A lot of heat storage in the city, less in the forest and savanna. So it's clearly why we have those differences. It's the heat storage. That's the main difference. That's the mechanism that leads to the higher air temperatures. It's not solar radiation and everything. Shadowing can be an effect, but mainly it's the storage and latent heat that make the difference, and that you see also here. You have this ramping up of the heat storage in the city while it is ramping up in the savanna and in the forest is much less. So we understand somewhere why this happens, right? So this is what we learned, up to 8% difference for a lot of cities. There's this ramping up leading to high temperature, and we have to study storage, heat storage, and latent heat. So what do we need to understand? Still, we have to understand why locally we can have so different climates. We should learn out of that how we have to design mitigation measures, and we also want to understand what is the impact of building morphology. Good. So that's the last part. First, what I want to show is that what is really why we have to simulate at this scale. So I will show you a simulation of the complete of a part of the city, this big domain here, without buildings, and then I will show you a simulation with buildings. And you see above the neutral boundary layer, and in the bottom the convective boundary layer. Convective boundary layer means there's much more heat coming in and there's much more buoyancy effects, which are coming in already. Right? So you see these big plumes, the yellow plumes. This is what is happening in reality when you have also, of course, some wind blowing these plumes away. What is important is that buildings themselves, because they heat up by radiation, they become heat sources themselves. And so they generate small scale buoyant structures, which have a big impact, or which also explain this higher temperatures that happen in the city. Even trees, the top of a tree where there's a lot of solar radiation becomes hot and works as a plume. Now, buoyancy has two effects. It only happens when it's hot, so that's what we don't want. But buoyancy also facilitates that you have heat removal. So it is negative because it's hot, but it's positive because it really makes that a lot of heat can be removed. But we made a model over the last 10 years. That includes wind flow at the billion scale, wind turbulence, radiation, long wave and short wave, heat storage and moisture in building materials. So you can have a material that becomes wet, or you wet it and it evaporates and cools. And we have also vegetation, trees and grass and other stuff. Okay, so it's a CFD runs model, buoyancy is included, radiation, heat and moisture storage, phase change, vegetation models. And you can, if you want, also model the rate to see where you have most rate on surfaces. John Ling developed several mitigation measures going from green roofs, reflective roofs, green walls, envelope insulation, evaporated pavement, cross-structure shaped, urban forestry, indoor cooling. And all this can be included in this model and studied as mitigation measures. Just to show you how we model trees, go very fast over it. So we model a tree as a porous media, where we introduce sink and source terms for momentum, heat and moisture. For radiation, the tree absorbs solar radiation. We can model it by ray tracing or by Lambert law. And we have, for long wave radiation from the trees to the surrounding surfaces, we have a heat factor. We model the sensible heat from the leaf. So the leaf, so there's a transport of moisture from the soil to the leaves. There are stomata that can be open or closed. When they open, there will be some transpiration, we call it. And so you will have a cooling effect due to the latent heat of evaporation. So because you have transpiration, you have cooling down of the leaves, that means also it has an effect on the sensible heat. And all this is included in the model. So we divide a tree in cells. In every cell there's a leaf, and for every leaf we calculate what is happening. Okay, we did this for Münsterhof in Zurich, for a square here. We take our boundary conditions from the mesoscale simulation. Okay, I don't go too much in the details, but we model in this square the heat and moisture transport. We take a heat wave, we focus on this day, June 25th. We have two solutions. One is a two-layer pavement, where we spray 6 milliliters of water, and then another solution is where we put some trees. You see here the simulation of that level. You see the wind speed, which is changing quite a lot. This is the river, which is a channeling of the flow, and sometimes the flow goes into the square here, and cooling effect. This is this entrance of the colder air from the river at that time, and you see if you plant trees, you have less cooling effect of the river. But of course, you have a cooling effect of the trees. You see the surface temperature over the day, left reference, right the vegetation. You see that of course the surface temperatures due to the trees is lower. We can look at different spots in time. Okay, so this is the surface temperature at 10. You see the cooling effect of the wet pavement. You see the cooling effect of the trees. Then you have the heating up. Here it becomes quite hot. As you see here, you have still a cooling effect of the wet pavement and of the trees. This is the zone where the reduction in air temperature is more than 2 degrees. Again, this 2 degrees. You see, we should go to 5 degrees, and many times we go to 2, 3 degrees, not more in air temperature reduction. So this is what we can do, not more. So that means if we have a climate change of more than 2 degrees, it means we have to adapt, and we cannot mitigate anymore. You see a big zone, so trees work very good. You have a big zone around the tree where it's cooler. The pavement that evaporates is more a local effect. We can calculate air temperature, wind speed, relative humidity, mean radiant temperature, and by that calculate a comfort index, universal thermodynamic index, index, which gives, as you see here, what you experience, what is your sensation. And you clearly see that by adding wet surfaces of vegetation, you can reduce from very strong heat stress to strong heat stress. So you can reduce by 4 or 5 degrees UTC. This is at 2 o'clock, the first one is at 12 o'clock. Very short about the spraying of water. I was 2 days ago in the Blue Mountains, and I saw that also there they collect water underground. In Katumba, there was a panel. I did not include it, but this is an idea that many cities have, that they have to store underground water, treat, of course, the water, see that there are no mosquitoes or whatever, and reuse this water for whatever need. What pavement system you have to do? I just show you one animation of the lattice Boltzmann simulation we do. So we can simulate at small scale how a material is drying. We can calculate how much evaporative cooling effect it has. And so that's how we design these 2 layers of material to make that the water that is evaporating gives the highest cooling effect. That you see here, you have the surface temperature. The surface temperature without spraying, and then spraying with different intensities. We are spraying for 2 hours, which is maybe not realistic. You cannot spray for 2 hours. But wait a moment, I will explain what we do. And we looked at the cooling effect. And what we found out is that if you integrate this difference in temperature without wetting and with wetting, this area here gives you what is the cooling effect. And we found out that the best cooling effect is for Switzerland, Zurich, 6 millimeters per day. And that you should spray them all between 8 and 10 before the sun comes on the surface. So to spray on a hot surface is not so good. You should spray it before. We then looked at if you could do something more realistic. So you can still wet with an intensity of 360 millimeters per hour. You can do this for 10 seconds. That means a truck is passing by slowly. And it does that 6 times. Then you get also this 6 millimeter. And you see we looked at if you have different times between passing of the car. We see that there's almost no difference with all those strategies. So you could really spray, go around your city, spray several times on hot surfaces, and this would lead to the cooling effect you see. The cooling effect is not so good as for trees, but in combination with trees it's very good. Where has the water to come from? It can be rainwater, but then you need storage. Drinking water is too costly, but you can also use grey water. And we just, because if you have high populated cities, there's a lot of grey water that you can use. Of course you have to treat it and eventually store it. We just did a study for Zurich. And the main thing is if you want to catch rainwater for Zurich, we have to catch it 30 days in front of the heat wave, and we need a cistern of 2 by 5 by 5 cubic meter for this area. And the water from all this roof was sufficient, so the surrounding roofs. So you can locally cool hot spots by having such a system. Last example, I go a little bit faster, is we looked at a project if there could be cooling from the surrounding mountains to the city center. And together with the city of Zurich, we designed different scenarios. This is the current situation. This is the corridor where the whole air from the mountain should come down. They wanted to densify it. That's what they proposed, and that's what we did. We proposed the same densification, but with buildings with much more gaps. So here the buildings are more connected. And we also added small trees and big trees. We looked at the hot nights. And you see here the simulation of the current situation, just a small part of the total simulation we did. And we look in detail on this spot here. And this is the densified one. And you clearly see that the temperatures increase. Okay, it's only 1 degree that it increases, but it clearly shows that building morphology has an impact on the air temperature, which is important for night why this change happened, you can look at wind, and you see that this street here is a wind corridor where cold air goes through. And we saw that when you densify the city, you put some high buildings, this wind flow through this corridor is blocked. And this is blocked by a tall building, so here you see the wind flowing through the street, and here you see that this building here at the corner deflects the wind flow and makes that this corridor of cold air is blocked. So small changes can have a big impact. What was very strange to see is if we change the trees from large trees to small trees, suddenly we could keep this as a corridor. So it's quite complex, and so you need quite detailed studies to understand what is really happening. So I come to my conclusions. So there are a lot of mitigation measures that can be done. We are still trying to understand which tree at which position we need. So what is the impact of 3 trees, how much you need, what's the distance, and this of course is different for every city and for different neighborhoods in every city. Should you combine it with green facades, green roofs, green spaces, parks, green shading, and so on, you have to take into account that trees, it takes quite some long time to grow. You have to take into account the water. So you need, even if you want to do evaporative cooling by spraying, so water is very essential to be taken into account. It depends on building morphology and also the background climate. Background climate means is it hot, humid climate, hot, dry climate, and so on. So that means there's still a lot of work to be done to understand. Now, one of the things of trees is that they are not optimal. They are fantastic machines that give shading and transpirative cooling. But during the night, they block long wave radiation to the sky. So at that time, the trees should be folded, should not be there. Also, it takes much too long time to grow. So we think that, of course, you need existing trees, but maybe you can also have some artificial trees. Well, there are some examples, like in Singapore, of such kind of trees, but I think there's still a lot to be developed. So bio-inspired artificial solutions. Also here, nano materials can be quite important to have also catchment of water and so on. So a lot of things can be here, the leaking and spreading and so on. This is something you have to design. There's a lot of ideas, especially in less developed countries, to use green balconies as heat exchangers. So balcony becomes a green oasis, and you use it as an exchange of heat, so it cools down the air that goes in. And of course, there are also the ideas of urban farming and so on. So these are all those possible solutions. The selection criteria are quite complex. It's not only on comfort and health, but it's also how much time it needs to implement. For instance, an urban forest can take 20, 30 years, while planting or making constructed shade only takes maybe 1 year. The cost compatibility between all this, so you cannot implement all these solutions at any place. Inequity, it is known that, for instance, in New York, that the poor neighborhoods are also the hottest neighborhoods because a lot of trees were cut and there were no mitigation measures implemented. So there's also a big question of accessibility to mitigation measures, which is for everybody. So this is a big issue. Acceptability. Not everybody accepts whatever mitigation measure. So this is also quite complex. We did a study with John Lynn of what were the most good solutions for a certain neighborhood, for a certain location. And for instance, 30 experts found that reflective roofs, insulated windows, evaporated roofs, and constructed shade were, for instance, for that location the best, and not trees or whatever. So a lot has to be studied. These are all possible combinations of solutions that you can have. So there's a lot of possibilities. And cities should implement a roadmap for implementation.
This is now from 23 to 2030, but of course it can be much longer. And you can have all these different mitigation measures, one after the other, that can be implemented. There is a lot of co-benefits of these heat mitigation measures. Not only the microclimate is improved, you can also have biodiversity, which is also quite important. It has impact on well-being, how people feel, how good, how happy they are, let's say. It has an impact on energy. It has also an impact on decarbonization, depending, of course, on what kind of mitigation measure you take, but a lot of them lead to a decarbonization. And what I want to say is we also work on resilience. I will not go through these conclusions. I think I explained them all. Just show you that we have two projects. One is on this resilience, to enhance the resilience of urban systems by combining engineering, design, and social research. This is with the Singapore ETH Center project. And we have a national project, Sustainable Living for the Individual and the Collectivity in the Energy Transition. It's a big title, but it was the understanding that if you want to do transitions with energy and climate change and everything, that well-being should be sustainable. And finally, I thank you for your attention and give you some questions.